We have gone over the definition of E and seen how it can be used for continuous compounding when we are looking for future value. So now we can do kind of different applications using continuous compounding. So the first two problems is still going to be about money, but we're going to be using the formula to find a different variable. And then the third one is actually going to be something completely different, but really cool, a different application. Okay, so how long will it take an investment of $10,000 to grow to $15,000 if it is invested at 9% compounded continuously? So again, the key words here is that it's compounded continuously. So you're going to use the formula A is equal to PERT. The other options would have been A is equal to P1 plus R over M to the MT, but this is not for compounded continuously. It's compounded for a certain amount per time, certain amount of times per year. So this is out. So we're going to use the continuous compounding formula. So let's write, so we have 4 variables. Let's see which ones we have and which ones we're looking for. So an investment is 10,000. That's the initial amount, so that's P. 15,000 is the future value, what it's going to grow into. It's invested at 9%, but remember that we can't put it like that in the formula. We have to change it to the decimal version. And then it asks you, we have 4 variables and we can see which one is missing, but another way to know that we're looking for T is because at the beginning of the question, it says how long, and long is T. So let's put all of our goodies in. 15,000 is equal to 10,000 E to the 0.09 T. Well, in the last video, we solved for T very similarly. First, you isolate the E. So we're going to divide both sides by 10,000, which is actually going to give us 1.5 on the left. And then this is when you have to use the inverse of E. And the inverse of E is to ln both sides. So we're going to ln. So on the left, it's going to become ln of 1.5. And on the right, the ln of E and E will cancel each other out. So we'll be left with 0.09 T. Right? So again, I can only do that because it's base E. So ln is also base E. That's where the key. And then to isolate the T, I just need to divide by 0.09 on both sides. And T is going to be approximately, it doesn't say here how many decimals places we should, but it's about, it says 4.50516. So we'll round to the nearest 10. It's about 4.5 years. Okay, that's a very high interest rate, 9%. So that's why it's growing 50% in 4.5 years. That's really little. That's a very good investment at 9%, actually. Okay, let's do another one about money. How long? Okay, so we're again going to be looking for T. Will it take money to triple if it is invested at 5.5% compounded continuously? So again, we're going to use, sometimes people say PERT, but of course you have to remember that the RT is in the exponent. It's not like everything multiplied. So let's write what we have. So the only number I really see is a 5.5%, which is R. But again, we have to write that. Oop, I should put a percentage. So how long will it take for money to triple? So it's a little bit tricky because it doesn't tell you how much the money is initially. It just tells you to triple. So for example, if I had 2,000, it would go to 6,000. If I had 10,000, it would go to 30,000. So if I have an initial amount P, it's going to go to 3P. But remember that the first step, which we saw here, is to divide the P into the A, right? So the first step that I did is I took the 10,000 and I divided it to both sides. So what's going to happen here, if we put in our formula, the A will be 3P. I keep P the same, E to the 0.055 T. And then when I divide both sides by P, the P's are going to cancel. So it's going to give you 3 is equal to E 0.055 T. And you could try it with these 2 examples and you're going to see 6,000 divided by 2,000, 3. 30,000 divided by 10,000, 3. So you don't need to actually know what the initial number is, because as long as you're tripling, when you divide, it's going to give you 3. So you can maybe guess what will happen if you were doubling or quadrupling and so on. So then we do the same process. We ln both sides. Ln of 3 is equal to 0.055t. We divide by 0.055. And when we do that, it's going to give us approximately 19.97. So that one will round to the nearest whole, so 20 years. So as you can see, it's taking now much longer. First, the interest rate is lower and you're trying to triple, which is more than what we were doing in the initial problem, or number 1, I should say. Okay, last one. Really cool concept if you've never heard about it. The continuous compound, okay, very important. Rate of decay, so now the interest rate is going to be negative because we're decaying, we're not increasing, of carbon-14 per year is given by this very long. And here they don't give it to you in percentage, they're already giving it to you in decimal. Otherwise, it would have a percentage with it. How long will it take a certain amount of carbon-14 to decay to half the original amount? So carbon-14 is actually used to find the age of really old artifacts. It's called carbon dating. It's a pretty cool concept. The only thing is that it's only able to be used for things that are about thousands to 10,000 years old. And to us, that would be like, wow, that's really old. But actually, there are things that are much, much older than that. So geologists will use carbon dating for around that time frame. But you can look it up. Very cool concept. So back to the question. How long? Again, how long? So we're going to be looking for T. So continuous compounding means we're going to be PERT. So we know our R. It's really long. Gotta be patient with it. How long will it take a certain amount of carbon-14 to decay to half the original amount? Okay, so this is very similar to number 2. So say, for example, we're talking about, say, grams here. So say if I start off with 20 grams, half would be 10. If I have 100, half would be 50. So if I have P, I'm going to have half of P. So I have half of P is equal to P, E, to the negative 0.001238. This is actually this is the actual rate of carbon-14. This is not made up. This is really what it is. We divide both sides by P, so this becomes 1/2 E to negative 0.01238. We ln both sides. It gets rid of the E. Oops, I'm forgetting the T. It's the little guy. Sorry, little T. And then we divide by this. And that will give us that T is about 5,599 years. This is called the half-life of carbon-14. So some of you maybe have heard of this before if you've taken, say, any chemistry classes. And there it is.